Transistors are easily one of the most game-changing inventions of the 20th century. They've made it possible to build lightning-fast, ultra-compact, and energy-efficient circuits, all while keeping costs incredibly low. In fact, if you're watching this on a phone, tablet, or computer, you're staring into a microscopic forest of transistors, billions of them, crammed into the tiny chips powering your screen right now. In this video, we're diving deep into the fascinating world of transistors. We'll start with the absolute basics and build our way up, covering everything you need to know to truly understand how these tiny devices work and why they're so powerful. A transistor is a solid-state device with 3 terminals and not a single moving part. That's a big reason why it's so fast, incredibly reliable, and built to last. When you look at a circuit diagram, you'll often see these symbols representing different types of transistors. They all follow the same basic shape, but with a few key differences depending on the type. Don't worry, we'll walk through exactly what each symbol means in the sections ahead. At their core, transistors work like electronic switches. Just like flipping a switch on your wall turns a light on or off, a transistor can do the same job, but without needing a human hand. There's no clicking or moving parts involved. Instead, transistors respond to electrical signals. That lets them switch things on and off automatically, silently, and at lightning speed. So say you want a light bulb to blink in a pattern, you don't need to sit there flipping a switch. Just upload a set of instructions to a microcontroller, and the transistor handles all the switching for you. Perfectly timed and completely hands-free. Now you might be thinking, wait, don't relays do the same thing? They can turn circuits on and off too, using an electromagnet to move internal contacts. That's true, but relays come with a few big drawbacks. First off, they're power hungry. It usually takes around 100 milliamps to energize a relay coil. A transistor? It can do the same job with less than 10 milliamps. And then there's speed. Relays are mechanical. They have parts that physically move. That makes them slow. If you need to switch something on and off 1,000 times per second, a relay just can't keep up. It takes time for the coil to magnetize and release. Transistors, on the other hand, don't move. No parts, no lag. They can switch on and off millions of times per second. No sweat. Now let's talk about the 2 main families of transistors, BJTs and FETs. BJT stands for bipolar junction transistor. These need a small amount of current to turn on, usually between 1 and 20 milliamps. They're great for amplifying signals and doing basic switching jobs, and they can operate at speeds up to a few hundred kilohertz. FET stands for field effect transistor. These are a bit different. They're controlled by voltage rather than current. That means they draw almost no input current at all, which makes them much more efficient. As a result, FETs can switch way faster, often in the tens or even hundreds of megahertz. But like with most things, there's a trade-off. BJTs are simpler and cheaper, which makes them popular in everyday circuits and low-cost designs. FETs, while more efficient and longer-lasting, are a bit more complex and tend to cost more. So they're usually reserved for when battery life, speed, or heat management really matter. In most basic electronics projects, you'll likely see BJTs. But when performance matters, FETs start to shine. Let's start with BJTs, since they're the most common type of transistor you'll run into when first learning electronics. Every BJT has 3 terminals. 2 of them work kind of like the ends of a regular switch. One connects to the load, the other to power or ground. These are called the collector and the emitter. The 3rd terminal is the control input. It's what decides when the transistor turns on or off. That one's called the base. Now, BJTs come in 2 types based on how they're built internally, NPN and PNP. In an NPN transistor, a thin layer of P-type material is sandwiched between 2 N-type layers. In a PNP, it's the other way around. An N-type layer is between 2 P-types. But honestly, you don't need to memorize the internal structure to use them. What really matters is the direction of current flow. In an NPN transistor, current flows from collector to emitter. In a PNP transistor, it flows from emitter to collector. That simple difference affects how you connect and control them in a circuit, and we'll explore that later. We always mark the direction of current at the emitter terminal. And that little arrow is super helpful. Just by looking at it, you can instantly tell whether the transistor is NPN or PNP. If the arrow points out, it's an NPN. If it points in, it's a PNP. A quick trick to remember? NPN, arrow not pointing in. One of the biggest differences between NPN and PNP transistors is how you turn them on. For an NPN transistor, the base voltage needs to be about 0.7 volts higher than the emitter. For a PNP transistor, it's the opposite. The base needs to be about 0.7 volts lower than the emitter. So if you have an NPN with the emitter connected to ground 0 volts, you need to apply at least 0.7 volts to the base to switch it on. But for a PNP transistor, if the emitter is at plus 5 volts, the base must be at 4.3 volts or lower to turn it on. It all comes down to the voltage difference between the base and emitter. Get that right, and the transistor does its job. When you're using a regular switch to control a load, like a light bulb, you can put the switch on either the positive side or the negative side of the circuit. As long as current flows through the load, it works. Transistors follow the same basic idea. For an NPN transistor, the current flows from collector to emitter. That usually means the collector connects to power or the emitter goes to ground. For a PNP transistor, it's the reverse. Current flows from emitter to collector. So you connect the emitter to power or the collector to ground. At first glance, it might seem like you could just use either an NPN or a PNP transistor to switch the positive or negative side of a circuit, just like a regular switch. Technically, yes, you could do that, but in practice, it's not quite that simple. Here's the issue. To control a transistor, you need to set the base voltage relative to the emitter. For an NPN, the base must be about 0.7 volts above the emitter. For a PNP, it needs to be 0.7 volts below the emitter. Now, when you're using an NPN transistor for low-side switching, with the emitter connected to ground, it's simple. Just apply 0.7 volts or more to the base, and it switches on. Easy. Same with a PNP used for high-side switching. If the emitter is at plus 5 volts, you just pull the base down to 4.3 volts or lower. Boom, transistor on. But here's where it gets tricky. If you try to use an NPN for high-side switching, the emitter isn't at a fixed voltage anymore. It changes based on the load, and that makes it hard to know exactly what voltage the base needs to turn the transistor on. The same problem happens if you use a PNP for low-side switching. The emitter floats, and your control signal becomes unreliable. So here's the rule of thumb. Use NPN transistors for low-side switching with the emitter connected to ground. Use PNP transistors for high-side switching with the emitter connected to VCC. Why? Because this keeps the emitter voltage steady, which makes it easy to apply the correct base voltage and reliably turn the transistor on. And just so you know, NPNs are more commonly used in beginner and microcontroller circuits. That's because they play nicely with low control voltages like the 3.3 volts or 5 volt signals from most digital outputs. Now that we've got a solid understanding of how to use NPN and PNP transistors as switches, let's put that knowledge into action. We're going to break down two simple light sensing circuits. One will turn on when it's dark, using an NPN transistor for low-side switching. The other will turn on when it's bright, using a PNP transistor for high-side switching. Let's see how each one works. To sense light, we'll use a light-dependent resistor, or LDR. An LDR changes its resistance based on how much light hits it. In complete darkness, its resistance can shoot up to around 1 megohm, but as light increases, the resistance drops, sometimes down to just a few hundred ohms. Now, when we connect an LDR with a regular resistor in this configuration, we create a voltage divider. That means the voltage at the center point depends on how much light the LDR is getting. In the dark, the LDR's resistance is high, so most of the voltage appears at the midpoint, almost equal to the supply voltage. As the light increases, the LDR's resistance drops, and the midpoint voltage goes down. Here's where the transistor comes in. If we connect an NPN transistor to this voltage divider, it turns on when the base voltage rises above 0.7 volts. So it activates in the dark when the voltage is high and turns off when it's bright. That makes it a simple darkness-activated switch. Now swap in a PNP transistor. This one turns on when the base voltage is about 0.7 volts below the emitter. So in a 6-volt system, that means the base needs to drop below 5.3 volts. And that only happens when it's bright. So this version works as a light-activated switch. You can even add a relay to either setup to control higher power devices, like a lamp or motor. And for extra control, replace the fixed resistor with a potentiometer. That way, you can fine-tune exactly how much light it takes to trigger the switch. Now let's take a closer look at the voltage current characteristics of an NPN transistor. This is where things get really interesting. A lot of students struggle with this part, so if that's you, don't worry, stay with me, and I'll break it down step by step. To explore this, I've set up a simple test circuit with 2 variable voltage sources, one connected to the base and the other to the collector. This setup lets us independently adjust each voltage and observe exactly how the transistor responds as we change them. We'll begin by keeping VCC fixed at 5 volts and then slowly increase VBB, the base voltage. As we do this, we'll track 4 key values that reveal how the transistor is behaving. In the first graph, we'll plot the base-emitter voltage and the base current. In the second graph, we'll look at the collector-emitter voltage and the collector current. Each of these measurements gives us a different window into what's going on inside the transistor as we adjust the input. Now let's start increasing VBB from 0 and watch how each parameter changes. Here's what the graphs reveal as we gradually increase VBB. VBE rises slowly along with VBB until it hits around 0.7 volts. After that, it levels off and stays nearly constant. That 0.7 volts is the threshold voltage, the point where the transistor starts to turn on. At first, IB, the base current, remains at 0, but as soon as VBE reaches that 0.7 V mark, current starts flowing into the base, and IB increases along with VBB. Meanwhile, VCE stays close to the full supply voltage, 5 volts, while the transistor is off. It acts like an open switch. But once VBE hits 0.7 volts, VCE drops sharply, down near 0 volts, just like a closed switch. And finally, IC, the collector current, stays at 0 until the transistor turns on. Once VBE reaches that threshold, the IC begins to flow. At that point, you can calculate the collector current using Ohm's law based on the collector resistor and supply voltage. So to sum up, when VBE is below 0.7 volts, the transistor is off. No current flows between collector and emitter. Once VBE crosses that point, the transistor turns on and begins conducting, just like closing a switch. The region where the transistor behaves like an open switch is called the cutoff region. The region where it acts like a fully closed switch is known as the saturation region. Now, if we keep increasing VBB, IB will continue to rise, but only up to a point. If we go too far, the current can exceed what the transistor is rated for, and that can lead to permanent damage. For small transistors, the maximum base current is usually under 20 milliamps. Power transistors can handle more, but either way, it's critical to check the datasheet and stay within safe limits. As long as we're within those limits, VBE will stay around 0.7 volts, and the extra voltage from VBB will drop across the base resistor, causing IB to increase proportionally. Now let's move on to the second part of our analysis. This time we'll keep VBB constant and slowly increase VCC to see what happens. We already know that if VBB is below 0.7 volts, the transistor stays off. Nothing happens. So let's set VBB to 0.71 volts. That gives us a VBE of about 0.7 volts, which turns the transistor on and allows a small base current, IB, to flow. Since we know VBE is fixed at 0.7 volts and VBB is 0.71 volts, that leaves 0.1 volts across the base resistor. Using Ohm's law, we can calculate the value of IB from that. Now let's see what happens. At first, everything behaves as expected. Because VBB is fixed, both VBE and IB stay constant. With VBE at 0.7 volts, the transistor switches on and behaves like a closed switch. As we begin increasing VCC, The collector-emitter voltage, VCE, drops close to zero, and the collector current, IC, rises, just like we'd expect. But as we keep raising VCC, something interesting happens. At a certain point, VCE starts to climb again. It's as if the switch inside the transistor isn't fully closed anymore. It's starting to loosen. At the same time, IC stops increasing. It hits a ceiling and stays flat, even though we're still raising VCC. Let's label this base current as IB1 and collector current IC1. Let's repeat the same experiment, but this time set VBB to 0.72 volts. VBE doesn't change much. It still holds steady around 0.7 volts, but the base current increases slightly. That's because, with VBE fixed at 0.7 volts, the extra voltage, 0.02 volts, now appears across the base resistor, RB, and that small increase is enough to boost IB. We'll call this new base current IB2. Looking at the graph, we see the same curve shape, but with some important changes. The collector current, IC, rises higher before leveling off. We'll call this new peak IC2. Also, VCE remains low for longer, only beginning to rise later as we continue increasing VCC. Try it once more with VBB set to 0.73 volts. And we see the same trend again. A bit more base current, a higher collector current, and a delayed voltage rise. Now let's repeat the experiment using real current values, and this time, we'll just focus on plotting IB and IC. If we set VBB so that the base current IB is 10 microamps, we observe that IC rises and then levels off at 1,000 microamps. That's 1 milliamp. Next, we increase VBB to make IB equal to 20 microamps, and now IC levels off at 2,000 microamps, or 2 milliamps. This pattern continues. For each increase in IB, IC climbs to a higher maximum value, each one directly related to its corresponding base current. Now, if we observe the IC plot, we can clearly see two distinct regions of operation. First is the saturation region, where the transistor behaves like a closed switch. In this region, as we increase VCC, IC also increases, just like current through a typical resistor or switch. But beyond a certain point, IC stops rising, even as we continue to increase VCE. It flattens out. This is the active region. Here's where things get interesting. If we plot IB against IC in the active region, we get a straight line. That means IC increases linearly with IB, and the scale difference is dramatic. While IB might only change by a few microamps, IC can change by milliamps. For example, a 10 microampere change in IB might produce a 1 milliampere change in IC. That's a current gain of about 100 times, and that's the heart of transistor amplification. A small signal at the base controls a much larger current at the collector. This gain is called the common emitter current gain, and it's usually represented by the Greek letter beta. Now, if we go back and look at each IC versus VCE graph, we can clearly identify the different regions of transistor operation. When we combine all those curves onto a single graph, the pattern becomes even clearer. At the beginning of each curve, there's a region where IC increases along with VCE. This is the saturation region, where the transistor behaves like a fully closed switch, and current flows freely from collector to emitter as VCC rises. In this region, VCE stays close to zero. But once IC stops increasing, even though VCE continues to rise, we move into the active region. Here, IC stays constant, and it's completely controlled by the base current, IB. So to summarize, in the saturation region, VCE is nearly zero, and IC increases with VCC, just like a switch that's fully on. In the active region, IC stays steady even as VCE increases. This is where the transistor acts as an amplifier, with small changes in base current producing much larger changes in collector current. Now let's try to combine the results of both experiments into one complete picture. We'll capture all these behaviors in a single graph of IC versus VCE. First, if IC is zero, even as VCE increases, the transistor is completely off. This is the cutoff region where VBE is below 0.7 volts and no current flows. Next, if VCE is close to 0, but IC is flowing, the transistor is acting like a closed switch. This is the saturation region where both the base and collector currents are active and the transistor is fully on. Then we have the region where both IC and VCE are non-zero. This is the active region. Here, IC is no longer just about VCE. It's directly controlled by the base current, IB. Finally, if VCE goes much higher than the rated value for the transistor, it will most likely fail and possibly burn out. This is called the breakdown region. It's beyond normal operation and should always be avoided. Most datasheets will clearly list the maximum VCE rating, and staying under that limit is crucial for safe and reliable circuit design. So putting it all together, this graph gives us a complete view of how a transistor transitions between being off, on, amplifying, and finally breaking down, all depending on the voltages and currents at its terminals. So far, we've looked at the ideal behavior of a transistor, but in the real world, things aren't always that perfect. For example, in the saturation region, VCE isn't exactly zero. Even when the transistor is fully on, you'll typically see about 0.2 to 0.3 volts across the collector and emitter. And in the cutoff region, where the transistor is supposed to be completely off, you might still notice a tiny leakage current flowing through the collector, usually around 1 microamp or less. These small imperfections don't matter much in basic circuits, but they can become important when you're designing precision or high-sensitivity electronics, like analog amplifiers or low-noise sensor systems. Now that we've covered the basics, let's explore how a transistor works as an amplifier. To make amplification possible, the transistor needs to operate in the active region. That's the sweet spot where it responds linearly to small input changes. To set this up, we keep the collector supply voltage, VCC, fixed, and we vary the base voltage, VBB, which controls the base current, or IB. As we saw earlier, changes in IB cause corresponding changes in the collector current, IC. And in the active region, this relationship is nicely proportional. Here's the key part. IC flows through a resistor connected to the collector, known as RC. According to Ohm's law, the current through that resistor equals the voltage across it divided by its resistance. This equation tells us how IC and VCE are related in the active region. And if we rearrange it, we get a standard linear equation, just like the format y equals mx plus c. In this case, the slope, m, is -1 divided by RC, which means the line slopes downward. Now let's look at the two ends of this line. If IC equals 0, then VCE equals VCC. This point is called the cutoff, where the transistor is off and no collector current flows. On the other hand, if VCE equals 0, then IC equals VCC divided by RC. That's the saturation point, where the transistor acts like a fully closed switch and the collector current is at its maximum. When we connect these 2 points on a graph, IC on the vertical axis and VCE on the horizontal, we get a straight line called the load line. This line shows all the possible operating points for the transistor in that particular circuit. And it's more than just a line, it's a powerful visualization tool that lets us predict exactly how the transistor will respond when we apply different signals. So now let's take this load line and use it to visualize how amplification actually works. To use a transistor as an amplifier, the first thing we need to do is set a steady operating point, a point where VCE and IC are fixed when there's no input signal. This is known as the bias point. Let's say we choose a VCE of 2 volts. According to the load line, that corresponds to a collector current, IC, of 3 milliamps. This value of IC comes from setting the base current, IB, to 30 microamps, which we control by adjusting VBB, just like we did earlier. Now let's vary the base current and observe how IC responds. If we gradually increase IB to 50 microamps, the transistor responds by shifting along the load line to match this new base current. As a result, IC rises to about 5 milliamps. Likewise, if we reduce IB to 20 microamps, The transistor moves to a different point along the load line, and IC drops to around 2 milliamps. So with just a small change in the base current, we see a much larger change in the collector current. That's the core principle of amplification. The transistor takes a tiny input signal, just a few microamps, and turns it into a much larger output current at the collector, measured in milliamps. That's what makes it such a powerful building block in electronics. There's one final concept we need to cover when it comes to transistors, and that's the bias point. As we've seen, before a transistor can amplify any changes in base current, we first need to set it up in the active region. That means choosing the right starting values for both VCE and IB, even before any input signal is applied. Let's look at 3 different bias points and see how each one affects amplification. In the first case, the bias point is set right in the middle of both the VCE and IC ranges. To place the transistor here, we set IB to 30 microamps, which gives us IC equals 3 milliamps, just like we discussed earlier. Now, if we slightly increase or decrease IB, those small microamp changes are amplified into clean, symmetrical swings in IC. This is exactly what we want from a well-biased amplifier. In the second case, the bias point is set too low. VCE is close to 0, right near the saturation region. Here, IB is set to 50 microamps, which gives us IC equals 5 milliamps, already near the circuit's upper limit. If we try to increase IB any further, the transistor leaves the active region and enters full saturation. At this point, VCE drops sharply, and IC instantly jumps to its maximum value, just like a fully closed switch. Once it's saturated, IC stops responding to changes in IB. So even if we continue varying IB like before, the transistor no longer amplifies the full signal. Only a portion of the waveform gets amplified. The rest is flattened or clipped. In other words, the output becomes distorted, and the signal is only partially amplified. With no headroom left for IC to increase, this bias point is not suitable for clean, linear amplification. Now let's look at the third case, where the bias point is set too high. VCE is near VCC, and IC is very low, putting the transistor near the cutoff region. To reach this state, we set IB to just 10 microamps. While this setup allows IB to increase and push IC upward, there's very little room for IB to decrease. If IB drops to 0, the transistor hits cutoff and IC drops to 0 with it. So this bias point restricts how far the signal can swing downward. Again, not ideal for clean amplification. So when you're using a transistor as an amplifier, it's crucial to choose a bias point right in the center of the active region. This gives your signal plenty of room to swing both upward and downward, without hitting saturation or cutoff, and without causing distortion. As a general rule of thumb, we place the bias point right at the midpoint of the load line. That means the collector-emitter voltage, VCE, should be around half of VCC, and the collector current, IC, should be approximately VCC divided by RC divided by 2, in other words, about halfway up the load line. This setup gives you maximum undistorted amplification, keeps the transistor operating squarely in the active region, and ensures your amplifier performs exactly as intended. And that's all for this lesson. I hope you now have a solid understanding of what a transistor is, how to use it as a switch or an amplifier, and the importance of the cue point in setting up a stable amplifier. If you find my content valuable and want to support what I do, you can encourage me by joining the Patreon community. And don't forget to like, subscribe, and stay tuned to ProbMad for more exciting and educational videos. I always welcome your comments and questions, and I do my best to reply as quickly as I can. But if there's ever a delay, I appreciate your patience. Feel free to reach out to me directly at shanilka.ariarathne@gmail.com. Thanks for watching, and I'll see you in the next video.